Good afternoon. So as I said to some of the people walking into the room, I don't have enough pixels to take advantage of this wonderful screen. As I've been talking to people over the last couple of days, I decided to modify my talk a little bit because there's some very interesting discussions going on in the hallways. I am going to talk a little bit about my work in astronomy. And I have a rather grandiose title that I sent Andrea about 3 or 4 months ago when I had landed in UT Dallas, where virtual humans is one of the big research areas. But in fact, as I've been talking to people, the first question I get is, what would motivate someone who's been living in Provence in the south of France for 15 years to move to North Dallas? And North Texas, I'm sorry. In fact, Mont Saint-Victoire could be seen from our bedroom in Aix-en-Provence, where we raised our children. There isn't a mountain until you get to Oklahoma or somewhere in North Texas. So I'm doing geographic acculturation rapidly. The second question that I get is, what the hell is an astrophysicist doing in a School of Arts and Humanities? So for those of you that have known me for a while, I originally got a bachelor's degree in physics at MIT. X-ray optics was my specialty. I started my scientific career at the very beginning of what was called X-ray astronomy. We used to go to White Sands, New Mexico, actually, and launch rockets. I went on to UC Berkeley and did a PhD in astrophysics, where we ran a NASA satellite that mapped the sky, very successful satellite. And then I went to France, where I became the director of a big astrophysics lab, where advanced optics was one of the big areas of research, and building instruments for the very big telescopes that are being built today. About 3 years ago, a colleague of mine that some of you know, Tom Linehan, contacted me and he says, "I've just started this program at UT Dallas, I want you to come here." And I said, "You must be kidding." I went there a few times, and what I'd like to do in the first few slides is just tell you what's happening at UT Dallas and why I decided to make a career change at the age of 61. And I'm now a full-time researcher in art and science after being a full-time researcher in astrophysics. The other anecdote I like to tell is, at the time I was interviewing at UT Dallas, my kids had left college and were interviewing for their first job. And so we were comparing notes on job interviews, and my eldest son the other day said, "Dad, I'm having a quarter-life crisis." And it says, "Well, that's great. We're totally synchronized. I'm having a midlife crisis and you're having a quarter-life crisis." So as I talked to Tom Linehan, who some of you may know was one of the first students of a man called Chuck Suri at Ohio State, who's one of the pioneers that started computer graphics in the 1970s and 80s. Tom shared with me his vision of what he was building at UT Dallas. It's the ATEC program there. It's a fully fledged art and technology program, totally joined at the hip with computer science and engineering, but the specificity is it's housed in the School of Arts and Humanities. Now that's sometimes the case for digital arts programs, but as you'll see, this is something that is of a different nature. And so what he wanted me to do is to come to Dallas and set up an art science program. And as you know, in this creative community, this community of practice that's in this room, since the 1960s, there's been rapid cultural appropriation of every technology we could get our hands on, you could get your hands on. But over the last 10 years, there's just been an amazing explosion, diversification of the terrains of science that artists are appropriating for their own uses. And so that's what I'm going to be trying to do over the coming years in Dallas. The program is Texas style. It started 7 or 8 years ago. There's an MA, a BA, MA, and MFA program. The PhD started last September. This semester we had 630 undergraduates, majors, and 160 graduate students, and the program is being sized for 2,000 students. So this is really a creative community dedicated to hybrid practices between the arts, science, and technologies. And so you're beginning to see from my enthusiasm after 35 years working with Leonardo, documenting the work of all you people in this room and helping promote art and science and art and technology, why this opportunity seemed to me in the end worth jumping without a parachute. We have a cluster of 9 faculty hires under process. I'm the first of 3 endowed chairs. We have a very major local philanthropic donor who's been endowing the program and will continue to do so. And there are a number of areas that have been developed there, games, serious games, virtual humans, a lot of work in simulation of various kind and animation. So it's a very ambitious technology program, and our plan is then to establish within that environment an art and science program. So my first requirement when I was interviewing, I said I want a double appointment as a professor of physics and a professor of arts and humanities. And it took about 9 months to get the 2 faculties to vote for my appointment. Those of you that are in universities know how difficult it is to get faculties to vote for anything. And so indeed, I'm in a position where I can actually have PhD students both in the School of Natural Sciences and Mathematics and the School of Arts and Humanities. So this is really a totally hybrid ambition. We can submit proposals to the NSF through the School of Natural Sciences or to the NEA through the Arts and Humanities. So really, we're really embedded in the university environment in a very ambitious and unusual way. The second endowed chair who will be coming in January is a man called Paul Fishwick, who's a computer scientist and will be a computer scientist in the School of Arts and Humanities. He set up the digital art program at the University of Florida, and some of you may know of his work in what's called aesthetic computing. He's convinced that artists and designers can change the way that computer science is done and in fact advance computer science agendas. And so he has a double appointment in Arts and Humanities in the Art and Technology program and also in the School of Engineering and Computer Science. So he'll be able to take PhD students both in computer science and in Arts and Humanities. The next person that I was able to convince to come to Dallas is a young researcher. His name is Max Schisch. He has a PhD in art history from Germany, but he's a born digital art historian. And so I jokingly tell him that he's going to do the post-digital humanities, because indeed he was born digital. And he's been working the last 3 or 4 years in a research lab of a scientist, Laszlo Barabazi at Northeastern University, applying the science of complex networks to very large databases. Now, he applies them to the databases in the arts and humanities, but he's so good at what he does that scientists come to him to help them analyze their databases. And so he really has developed a transverse research practice between, in this case, art history and scientific disciplines that are faced with the problems of large databases and how to detect underlying patterns and trends and so on. So he'll be coming in January also, and I'll be working with him to set up some research groups also with scientists in natural sciences. The third person that I was able to convince to come to Dallas was Scott Gresham Lancaster. Some of you from the Bay Area will remember the group called The Hub. He was a member of The Hub, very early experimental music practitioner, but in recent years has been working on the sonification of data. I've collaborated with him when I was in Marseille on the sonification of scientific data. And so we're going to be working with him to develop tools to navigate through very large data sets. And so I'm very excited that both Paul, Max, and Scott will be at the university beginning in January. As I mentioned, one of the major research areas in the program at UT Dallas is on virtual humans. This is an area that comes out of the serious gaming industry, which comes out of the gaming industry. And just 2 quick examples. On the right is a project funded by the Gates Foundation. He's been asked to simulate a high school with 50 different high school students, each one with different personalities. The virtual characters interact with each other as well as with you. And so they're busy texting to each other. So if you tell one person something, it spreads through the group of students. It's interactive dialogue, branching narrative. And the idea is to have each one of these characters, in fact, right now they're doing motion capture of a number of different high school students so that they have the whole variety of body language appropriate to different age groups and people. And the idea is to create a training environment for teachers. And so indeed it's kind of a problem setting environment and very, very rich area of research that of course can be applied to many, many different areas of application. On the left is one of the medical training applications that they've been using this system for. This is for neonatal care, for treating babies with respiratory diseases. And so basically it's a hospital environment. They have simulated babies. You can see the baby in the cot. And depending on the symptoms that the baby has, then the person who's being trained has to identify the symptoms, treat the baby. So the idea of the game, of course, is to keep the baby alive. And so this allows, in the training environment, medical practitioners to encounter very rare diseases that they might not encounter very often in their practice. And it also allows them to improve their diagnostic skills. A number of different applications of these virtual humans, and that's why the word avatar ended up in the title of my talk. Never done research on this kind of stuff, but what's interesting, I think, is the 10-year vision that the group there has of the kinds of sophistication that's being developed as we develop online virtual interaction humans that we collaborate with. And so I'll come back to that a little bit later. So that's why I am at UT Dallas. The second part of the question then is, what the hell is an astrophysicist doing in School of Art and Humanities? Well, obviously, because of my involvement with the Leonardo organization over the last 35 years, I've been very embedded in this research community. One of the concerns that we all have is, and in fact, I was going to ask how many scientists there are in the room. How many scientists are there in the room? Okay, we got a problem. There are 6 of us, 7 of us. So indeed, we're trying to build hybrid practices that connect the arts and sciences and arts and engineering together, but in fact, we're social human beings and we tend to cluster likes with likes. And so I think one of the key problems is how we embed our activities in different ways in scientific research. And so it seemed to me that rather than just taking a position as a professor of physics, which I could have done, I really wanted to have this hybrid embedding in both schools. So let me just come to one of the topic areas that I'm going to be working on, and many of you in this room are expert in this area. It's currently called the big data problem, although that problem's been relabeled once every 10 years over the last 30 years. But when I was a graduate student, I had colleagues in graduate school who used to study one galaxy at a time, and they'd write a whole PhD thesis on it. Take them 5 years, 6 years. Now we have online access. In this case, this is the largest online catalog of galaxies. There are over 500 million galaxies in it, the Sloan catalog. The catalog is growing. And so indeed, there are people who now analyze 100 million galaxies at a time. And that is a shift that I've lived in my research career, seeing this happen, being involved in helping it make it happen. With NASA, I helped develop what I could now call virtual observatories, where we could all pool this astronomical data and put it online. An example of where we're headed is, there's a Pan-STAR telescope being built in Hawaii at the moment. It will photograph the whole sky 3 times a night, and it has a camera that's 1.5 gigapixels and is about 2 feet by 2 feet is the size of the camera. So you take your CCD from your cell phone and just spread it out on 2 feet by 2 feet. That telescope is going to be pouring data every night at such an incredible rate that it's transformative in the kinds of science that will be done. I won't go into the details of what kind of science that telescope is going to be able to do, but it can do research that nobody could do before because of the way that it's going about it and the collection capability. So we've gone in my lifetime from one galaxy at a time to access to billions at a time. And in this case, the telescope is powerful enough that it will look back in the universe to roughly 3/4 of what's called the look-back time, the light travel time through the universe. And so indeed, something really profound is going on in scientific disciplines. I saw that happen in astronomy. Of course, it spread to other fields very quickly, genomics. And now, of course, governments have the problem and businesses have the problem. And it's now called big data. And there are companies that are happy to sell you their services to analyze billions of records. A few years ago, a friend of mine, Daniel Boston, who at the time was the Librarian of Congress, gave a speech at the World Space Congress. And he realized what was going on at the time. This was 1992, I think. He spoke to the World Space Congress, and he just said, you guys, you don't realize what's happening under your feet. We're going from a period of science that was data poor and meaning rich, this is Dan's words, to data rich and meaning poor. And he called this epistemological inversion. And in fact, in his inimitable style, he also said to NASA, since you don't have time to analyze all your data, my first recommendation is you stop taking data and analyze it and think. Of course, NASA didn't take that recommendation because they like to build telescopes. But indeed, Dan, who was a historian of science and technology, realized that something very deep was changing under our feet, that was transformative, that was changing our relationship to the world, and of course the way that scientists are doing their work. You've all seen these charts. This, in this case, is the amount of data being collected by satellites looking at the Earth. 2004, it's not even a blip on the chart. There was so little data being collected. And now that's the projection to 2020. So indeed, we're getting more and more data per year about the Earth, which of course is being fed into our understanding of the Earth's environment. And it's no accident that it was in this time period that we suddenly realized the climate was changing. The climate has been changing for a while, but until you have this quantity of data, it was very hard to marshal the arguments to convincingly demonstrate global warming. One of the interesting things in this chart is the very light blue bar at the top of the bar charts. I need Al Gore's ladder. The light blue charts are not data about the world, it's simulated data. It's pretend data. It's data generated by models. And so in fact, the thing that's growing the quickest in that chart is not data about the world, but simulated data. Now, of course, if you're in the gaming business, you know that, right? I mean, the amount of gaming data being generated today is incredible. And so not only is the amount of data about the world growing very, very rapidly, but the simulated data that we create is growing more quickly than the data about the world itself. So what happens when you start getting a lot of data? It really changes the way you do things in a number of ways because it's not just more data. When Charles Darwin had to convince people that he knew what was going on in evolution, he had to take a bunch of boat trips to go collect his data. It took him a long time to find the right birds and turtles, make drawings of them. And in fact, his old data set fit on a couple of shelves in his library in England. Today, in fact, and I haven't checked the numbers, there are more astronomers analyzing the data that have never looked through a telescope or taken data through a telescope than actually take data. So the profession of data analysts is growing as quickly as that data flow. And so that changes, in Dan's words, epistemology, the way you know something and how you convince people you know it. And that's really, we're living in the middle of it. And I think 50 years from now, the historians of science will be able to write the story. But when you have a lot of data, it pushes you to different kinds of mathematics. When you don't have very much data, you tend to write equations. You can't do an equation for climate change. So what you do, instead, you use mathematics to create simulations. And in fact, you make simulations of the world, and then you compare it with the world. And what's amazing now is a simulation has the status of a scientific theory. If you have a really good model and it looks like the world, then you convince your scientific colleagues that you understand what's going on. Now, 100 years ago, that wasn't the case. You know, you had to figure out how to do a different kind of mathematical analysis. And so that's a real change in the way that science is done. The scientific method is not a stable method. It evolves, in fact, over time. And that change has happened over the last 30 years because of access to computer simulation. The other thing that happens is when you have a lot of data, you just look for patterns and trends. And in fact, a few years ago on the blogosphere, it was the end of theory. Who needs theory? All we do is we look at all the data and we extrapolate it. And that's good enough. Of course, then the stock market crash happened, and I don't know who the end of theory guy was, but clearly there are some data sets you cannot extrapolate to predict how the world is going to behave. But pattern recognition has become an industry in itself, of course, because when you have large data sets, then in fact you can look for trends, and in some cases it's very good. And so there's now an industry called the trend spotting industry, as you probably know, that's beginning to appear, which is just beginning looking at the whole web. The most famous example, of course, that everybody knows is that when you get sick, you start Googling with your symptoms, and in fact, Google knows before your doctor what you're sick with by 2 to 3 weeks, because you tend not to go to the doctor until you're really sick, but you start Googling a little bit earlier. And so indeed, there are now trend spotting algorithms out there that can just look at what people are doing, look for patterns, and predict what's happening. And of course, the business world is right on top of that. When you have a lot of data, you can ask questions that you couldn't ask when you didn't have much data. I always like to joke that if you're a PhD student in college for 3 or 4 years, if you study something that happens once every million years, that's probably not a good choice of a research topic. You know, you may have to wait a long time until you can study something. What it means is when you don't have a lot of data, you tend to study things that happen often. When you have a lot of data, you can start looking at things that don't happen very often. And so there's kind of a shift of attention just because of the very large data flows. Some people call this technologies of attention. It shifts your attention to other research agendas. And of course, this happens under your feet. You may not be aware of it, but there are all kinds of research questions that you can start asking when you have a lot of data as opposed to when you didn't have very much at all. Of course, every data set has blind spots. And I learned a phrase from a young artist this morning, Julie, I forgot your last name, data cloaking. What was her name? Julie Freeman, are you here? Data cloaking. Everybody hides some of their data, right? Because you can't deal with all of it. So you have to decide which data to cloak and which data to show. Now, of course, scientists, that's a well-kept secret, right? You're getting rid of the noise in the data. But of course, different people have different interests in the same data set. And so one has to be very aware that in all big data sets, biases are built in at a very fundamental level. And so one has to be very careful. The other thing, of course, is it's often easier to get funding to analyze data to get new data. So what tends to happen is you analyze the data you have, even if it's the wrong data. And so you have to be very, very careful about whether your strategy for understanding something is being hoodwinked by the availability of data when it may not be the data that you need. And then, of course, in the humanities, there's a huge debate around the digital humanities, because in many areas of scholarship, you cannot quantify major concepts. And so how you bring qualitative data and qualitative thinking into the big data era is a real challenge. And of course, the humanities scholars are struggling with this because the obvious example is stories are not not very well encoded in data sets. And so if you're interested in the evolution of mythology and human culture, good luck. And it's much easier to ask how many people are online on Warcraft at a given time. Other issues that happen as data becomes plentiful, of course, new kinds of technical problems, and people are aware of this because we're now all being besieged with cloud computing technologies, which of course physicists at CERN and other places pioneered. But indeed, you start running into other kinds of technical issues. A big issue right now is not really a big data problem. Often you don't need all the data, you need a little piece of it, and you want it on your cell phone. And so the real problem is mobilizing a little bit of data out of this cloud of gigaflops of data, gigabits of data. And as someone said yesterday from Los Alamos, or Tuesday, it's so expensive to move the data that you're better putting off the disk in a truck and driving it across the country when these data sets get that big. And so indeed, how you access a small part of data in a very large data set becomes a challenging technical issue. There's also a transformation that occurs because you have to start thinking of data as a fluid, not as an object. And in fact, most people think of data as something that's kind of a fixed thing. Now, of course, in the computer animation and special effects industry, we know differently, but that is a transformation that changes the way that you attack problems. And I think many people tend to try and visualize data as objects when in fact it's a fluid and you need different strategies. So, of course, immersion in data, illustration of data. The final thing, of course, and as I mentioned in the previous panel earlier this afternoon, the other thing that's happened with large data sets is the open data transition. Now, I lived through this in astronomy because NASA and the National Science Foundation decided that any astronomer that took data paid for by the US government had an obligation to make it public. And so, in fact, all NASA contracts right now have a clause in it that the scientists must make their data public. Now, that happened in astronomy, and it's rippling through other areas, hotly contested in the commercial world, needless to say, but at least when your research is funded by the government, that obligation to make it open seems to be an important one. That led to the phenomenon of citizen science. Over the last 10 years, there's been a proliferation of various citizen science projects exploiting the fact that data is available freely online. So now I'm going to have to credit Ruth West. Are you here, Ruth? We were discussing this at the SARC meeting in Santa Fe on Tuesday. I hadn't called it a crisis in representation because I'm always cynical of people who say there's a crisis. But in fact, there is certainly a point of rupture, I believe, going on, where because of the things I've described up to now, we're really seeing a whole range of issues of how you go about representing what's inside data in ways that human beings can do something with it. This has happened in sort of two waves in the 1990s with scientific visualization and the first visualization labs that were developed. But of course, it's now happening in a really big way because this is now touching other sectors of the economy. And so there are just a proliferation of conferences on data journalism, biovisualization, infovisualization. And so there seems to be really a transformation going on where we don't really have an understanding, and this is where maybe the arts and humanities have a role to play, of how you go about with these very, very large data sets of figuring out systems of representation, all the data cloaking issues and all the biases that I talked about before. And so here maybe is an opportunity for the arts and humanities to work with the science and engineering. Just wanted to mention a couple of people in this. So in 1989, Leonardo gave a prize to Donna Cox. That sounds like 7 generations ago now. But indeed, she, as an MFA graduate, started working with scientists at the National Supercomputing Lab, helping scientists visualize scientific data. And she's the co-author on a number of papers with astronomers on black holes and star formation and so on. And she's also been one of the major developers of planetarium shows with fly-throughs and the universe and so on. And so indeed this was sort of the first wave of the crisis of representation, where suddenly some artists found themselves working with scientific teams to represent the data, help the scientists represent their data. So this is not a problem in illustrating data, but really, and this is something Donna has really argued from the beginning, is that you need the artists involved at the beginning of the process, because indeed it's a collaboration, she calls it Renaissance teams, where the interaction with the people who are going to represent what the content of the data is so that other people can understand it are actually embedded in the scientific research group. Earlier this year, I went to the Alisphere at UC Santa Barbara. It's housed in the Nanosciences Institute. It's a very large state-of-the-art visualization facility. Of note is the director is a professor of music, Joanne Kuchera-Morin. And so indeed, there's a second example, and this is a second generation visualization facility. And over the last couple of years, I've been visiting a number of these places. The kind of projects they're doing is interesting because you find both artists and scientists working in the same environment. And of course, that happened with the home PC. Suddenly, scientists and artists and musicians were using the same tool. But this is now state-of-the-art, really. Now, for the pioneers in the room, you'll remember 30 years ago how difficult it was to get access to the state-of-the-art scientific facilities. This one's run by a professor of music, and the artists are in there doing research at the same time as the artists side by side. So that really is a sea change within our community. So what happened? Okay, I'm going to change pace here a little bit. So what happened to astronomy as it entered the big data era? And some of you have heard me give this talk before, but I'm going to give it in a slightly different way. Okay, it was really embarrassing because in the last 10 years, 20 years, astronomers have realized that if you look at an image of the sky, 95% of the content of that image emits no light whatsoever. It's dark. Now that's a little bit embarrassing. That means astronomers have been working for 100,000 years, and they've been looking at 3% of the universe. And yet we claim to be the world's expert on what's going on. It's like we've been studying the decoration on the universe, but the real stuff, the stuff that's going on, doesn't emit light. And that's really bad luck for astronomers because we don't know how to measure it. We can see its effect. It emits no kind of light. And more embarrassingly in the moment, we don't know what the hell it is. We don't have a clue. Well, I'm exaggerating a bit because a colleague of mine got a Nobel Prize this last year for what's called dark energy. So he detected that if you look at these images going far back enough in time, not only is the universe expanding, but its rate of expansion is accelerating with time, which is totally counterintuitive. It's like there's a force of anti-gravity at work. Well, he and two of his colleagues got Nobel Prize in physics. It's probably the first Nobel Prize that's truly for admitting total ignorance. They discovered that most of the universe is full of something. We don't know what it is, but they got the Nobel Prize. Now, astronomers are pretty confident animals, so we still submit proposals to the National Science Foundation, and we claim to be experts on what's going on. But the fact is, 95% of the content of the universe does not emit any light of whatsoever. Now, most scientists would have confidence, well, this is a temporary glitch. Give us a few more $1 billion and we'll figure it out. And maybe that's the case. As you know, CERN just discovered the God particle, or whatever they're calling it. It took them 30 years, thousands of scientists. To get to the bottom of this mystery is certainly going to take the same kind of investment and time. And so, let's hope my colleagues are right. We understand the universe so well that we can simulate it in a computer. The biggest supercomputers on the planet have been used to model the evolution of the universe. And it's amazing. You run the simulation, you compare it with the galaxies and we see, we understand it completely. And so some of you have heard this talk before. I'm going to show you the history of the universe in 8 seconds. It's about 14 billion years, compressed a little bit. And this is an amazing scientific feat. These simulations, done on the biggest supercomputers on the planet, when you run them and compare them with the universe as it is, you get a really, really good match. So here we go. So that's from the Big Bang till today. If you analyze step by step the way structure developed in the universe, you compare it with the structure that we see with our telescopes, it's a perfect match. Clearly, we understand what's going on. What you can also do is take the same data and sonify it. I couldn't find the file for the whole history of the universe, so I'm going to play you the first 100 million years of the universe. But I'm going to ask you to close your eyes, because the problem is your eyes dominate over your ears. So please close your eyes and listen to the first 100 million years of the universe. Same data, one is a visualization and one is a sonification. The model is amazingly accurate in modeling how the universe looks like over the last 13 billion years. The trouble is, of course, we don't have a clue what dark matter and dark energy is. So we're looking at what the decoration in the universe is doing, we're modeling the rest of it with something that we don't know what it is, and we say, we got it, give me some more funding. So is this just an example of where science will progress and will slowly have an increasing scope of knowledge about these phenomena? Or is something deeper going on? And I'm treading on thin ice here. The 7 scientists in the room can attack me at will. But it seems to me that, in fact, modern science doesn't make common sense, for a very simple reason that most of the ways that we study the world today comes through scientific instruments and not through our senses. And most people don't have experience with mediated senses. And so, of course, one of the things that technological artists are doing is mediating that data in a very, I think, constructive and important way. The anecdote I always like to take, and I apologize for those of you that have heard this before, but I have every instrument I've ever built hallucinates. And if you're a scientist, you know exactly what I mean. Sometimes you run the thing in the lab, and something weird has happened that day. The image is screwed up. You don't know what to do with it. You replicate it, and you don't know what to do with it. Of course, as an instrument builder, you get really good at figuring out when your instrument is hallucinating. But most people don't have that experience. So when is an instrument fabricating data, and when is it actually mapping things from phenomena into your sensory awareness? And so I think we underestimate the impact that this has really about how we understand the world. And as I said before, a lot of science now is done with experiments on data rather than experiments on the world. Most of the world is not on human scales. Nina Zegledy and Ramon Gardens, I think Nina's here, have written about this a fair amount, which is, when you start talking about quantum mechanics, we don't have a clue what we're talking about. You probably think an atom looks like a billiard ball. Well, atoms don't have edges. They're fields in space. We have no experience with things at that scale. Same goes with the scale of the universe. And what that means is, because of our lack of experience, it means our intuition, which we develop as children, the languages we develop of naming things that we are in our world, the metaphors and stories we tell about things that we can identify in our world, are just built on the wrong data set for understanding those kinds of phenomena. Now, of course, scientists have used mathematics to guide them through that kind of a process, but it's really, really not clear. So I think a really open question is, as we go forward in this large data era, we multiply the way the instruments monitor the world. One of the things that artists can be doing is developing ontologies, naming things, developing languages, way to talk about things that they have experience with. In the panels here, we've seen artists taking environmental data, biophysical data, all kinds of data, developing that kind of human intuition that allows you to talk about things and name things, and eventually develop systems of representation. Now, how deep this problem is, who knows, but I'm willing to bet on it. I always like to say that one of the things that artists are doing today is making this kind of science intimate. They're taking data, and as I said in the previous panel earlier this afternoon, in a very real sense, we're becoming a data-taking culture. And I think that's a very important cultural shift. About 2 months ago, MIT Press published a Leonardo ebook on the Sublime in art and science. I don't think I'd ever used the word sublime in 50 years. It was kind of one of those esoteric words that lived in humanities and Kant and stuff. But we had a really interesting discussion about what happens when you're at the really edge of understanding things. You know, wouldn't it be frightening if it was basically not understandable? And I think we're sort of in a point in time, we could argue, that is a little bit like the 19th century. For those of you that know your history, I mean, beginning in the 1850s, there was a cultural shock that it's hard to estimate the impact of. The discovery of X-rays, electromagnetism, all these phenomena that the senses couldn't detect, but scientists would prove that exist. And so indeed, you know, the romantic movements of the end of the 19th century were coupled with scientists who really were deeply culturally perturbed about what they were discovering with these phenomena that were not accessible to the human senses. And so, you know, as I was discussing with Sundar Surukai and Michael Punt and the other people for this ebook, well, what if we're so badly designed that we'll never understand the universe? I mean, you know, scientists are not going to admit that very easily. But clearly science is driven by human beings who can understand certain kinds of things. What happens if fundamentally we're just not designed the right way? And clearly, as I said, in astronomy, we're designed the wrong way. 95% of the universe doesn't emit light. So if you want to design a human being that is an astronomer, don't give them eyes, give them something else. Because it's the wrong sense to understand astronomy. What happens if there are really fundamental untranslatables, things that cannot be translated? At UT Dallas, one of my colleagues runs the Center for Translation Studies, and actually there are experts in these questions. You know, between cultures, there are certain concepts that are not translatable. So as artists and scientists begin to work together, what happens if there are things where we'll never be able to talk about the same thing? Fundamental untranslatables. Now, of course, scientists are very used to unknowables. You cannot know what happens inside the horizon of a black hole. You will never know what happens to what falls into a black hole. You will never know what happened in the universe further away than the light travel time of the age of the universe. But what if there are some fundamental unknowables? And certainly, when you start taking big data, maybe you're going in the wrong direction. For those of you that are familiar with Thomas Kuhn and his discussions, he talked about how between different scientific theories, there were things that were just not compatible. And that's why he talked about paradigm shifts, that science couldn't just evolve progressively. At some point, you had to take a jump, and the new theory was incommensurable with the previous one. And so, you know, since I'm at UT Dallas where they design virtual humans, I've just asked myself a stupid question. Maybe we need to design virtual humans with the right senses to understand the universe. And of course, the virtual humans online could interact with all the big data. We could design them with senses optimized for that purpose, and then we could collaborate with the virtual humans. Now, maybe that's 50 years from now, but who knows? So I'm just going to end now with a bit of a slightly different discussion in the last 10 minutes. Because one of the joys of being here, I was at the first ISEA conference. Who else was at the first ISEA conference? 7 of us. Some of us were at the first SIGGRAPH conference. I wasn't because it was in someone's hotel room, as I remember, but or something. You know, the wonderful thing is that people you and I know in the 1960s and 70s developed all of computer graphics and animation, the gaming industries. I mean, we succeeded. Art and technology succeeded. And now we're occupying new terrains. And so just a couple of observations. For my sins, I sometimes sit on governmental advisory committees and review panels. One of the things that's happened over the last 15 years is that both the US National Science Foundation, but also the European research funding organizations, and I just reviewed 5 such proposals last weekend, are getting strange proposals from schools of art and design and schools of art and humanities. Sometimes the goddamn proposal is undistinguishable from the proposal received from a school of science and engineering. Now, often these are collaborations and so on, but clearly this was not happening 30 years ago. You did not get proposals at the NSF from schools of art and design. And so there's just a phenomenon that is happening. The Rhode Island School of Design has a director of research whose job it is to get extramural research funding, and they're doing things like reimagining medical communications research. So indeed, institutions in arts and humanities are evolving very rapidly. There's a dramatic growth of professionals with hybrid careers. And I don't have statistics on that, but I've been working with Robert Bernstein, and we're trying to quantify these feelings. But this is people who maybe for a while were in music and then were in working for Sony Labs or something. You know, there are these people that over their career have migrated in different contexts, which would be normally viewed as arts and design or science and engineering. And I had a student in my class in Dallas, undergraduate in literature, MA in biology. You know, what the hell's going on? As I said, our program at UT Dallas is that, so what's going on? Lisa Randall, who's one of the leading researchers on string theory, is collaborating with artists. She had an opera at the Centre Pompidou this year, earlier this year. She talks about what she's doing is translating the world of theoretical physics in a way that appeals to scientists. So her target audience isn't the general public, it's her peers. I remember Joan Chikagawa, that some of you know when she was at Rockefeller. She said, Roger, this was 20 years ago, this earth science stuff, it's second-rate artists working with second-rate scientists. You know, let me tell you, Lisa Randall is a top-rate scientist, and she has time to work with musicians and composers to develop a multimedia opera to translate her theoretical physics in a way that appeals to scientists. So that something is really changing in our environment. So what do institutions do when something's going on? You go commission a report. So in the 1990s, clearly the phenomenon was IT-centric. The emergence of computer graphics and animation, scientific visualization, human-computer interface, the creative industries discussion in England, Australia, and a number of other countries. The report that was finally put out was the late Bill Mitchell's report called Beyond Productivity, and it documented a critical mass of research practice that led to new funding mechanisms such as the Creative IT program at the US National Science Foundation. And in fact, this happened in Europe, in Australia, and a number of other places where there was a realization that art and technology practitioners were developing research that was critical to national interests and should be funded. About 10 years ago, and I think all of you, I've just been going around the panels here, about 10 years ago, the phenomenon started spreading beyond IT to biology. You know, Symbiotica appeared on the scene in Australia, to medical, to ecology, to the environment, to nanophysics, if you look at the UCLA program. I just put up one example. Diane Gromela, who's an MFA, is establishing right now an Institute for the Study of Chronic Pain at the University of Vancouver. And so indeed, something that was IT-centric has spread to other areas of scientific research and development. So it's time to go commission a report. So the NSF and the NEA over the last couple of years in the United States have been convening this community, a number of workshops, to try and figure out what's going on and what to do about it. The NEA recently announced some programs they were doing with the National Institute of Health in the USA, and this is also happening in Europe. Of note is indeed what's going on is interesting different divisions of the National Science Foundation, not only computer IT, but also physical sciences, biological sciences, social sciences, education, and so on. And in fact, this year a program was set up to specifically fund programs that were hybrid between several divisions of the NSF. Coming out of this, Carol Lafayette, who I think is in the room also somewhere, and colleagues, Carol Strohmaker and Gunan Nadaranj, submitted a grant to the NSF for what's called an EAGA grant. And this is funded through next summer. And I, with Carol, are chairing what we're calling an advocacy white paper. And we're developing a study that will be submitted as part of this EAGA grant in June of 2013. And one of the things we hope to do is motivate with evidence that, in fact, what I've been saying is happening, that this growing earth science technology research community is contributing to things that are of national importance and critical today, and hopefully that we identify ways of accelerating and supporting this research community and the artistic community that's embedded with it. What we decided to do, I participated with the National Science Foundation in what I call the astronomy decadal surveys. Every 10 years, astronomers do one of these studies. And what they traditionally do is an open call to the community for input. So we put out a call. We thought it was going to be a summer project. We might get 20 replies because everybody, you can't put that on your CV and your tenure application. We're up to 90 abstracts for white papers. We'll probably have 100 altogether. The papers are due November 15, and we have a steering group that's going to try and synthesize all that into a final report with suggested actions, both to look at obstacles facing people in our community and new opportunities that really need to be seized. And the traditional obstacle for those of us that are in academia is that the people with hybrid careers have a hell of a time getting promotion. Because indeed our universities don't know how to handle these people. But there are other problems which have come up here, is how we couple what we're doing to community groups and other groups outside of the academy, and there are many obstacles to doing that. So hopefully this process will lead to something that may convince the National Academy of Science here to do a national study that really documents this in depth. One of the interesting things that's really emerged over the last 5 years, and a lot of you in this room have contributed to this, is what in the US is called the STEM to STEAM movement. STEM is science, technology, engineering, and math education. There's now a realization, I think, in this country there are like 600 or 800,000 jobs unfilled because there aren't enough American applicants who have sufficient technical or scientific skills. So whatever we're doing, we're not filling the employment needs of whole areas of the American economy, and this is the case in Europe and other countries. And so there's an argument that, in fact, if you can integrate arts, design, and humanities into STEM, maybe you can reach out to young people that maybe not turned on by the math as such, turned on by other things, and in the process realize that they have to learn how to do computer science or other skills. And in fact, many of you will remember, and there are probably people in this audience who were going to go to art school at the beginning, or maybe did, and then shifted. So there's very good testimony online from John Maida in the Rhode Island School of Design that makes this case. This argument is playing out in Europe and other countries. I'm out of time. So we have a STEAM working group that Carol Lafayette has put together. Lucinda Presley, Brian Smith at RISD, Catherine Mariwaki, Alicia Gibb, and Tracy Hammond. And basically this is really an open, bottom-up process of trying to identify obstacles and opportunities. Here's just a map of where the white papers are coming from, which immediately tells you we have one problem, geographic. So we have nobody in North Africa, and I know of really good art and technology groups in North Africa. They're probably busy doing other things right now than responding to calls for white papers. We have nobody in Russia, kind of strange. Very good art, science and technology groups in Russia. The second problem we have is we have almost nobody from industry. In fact, how many people here in this room work in high-tech companies? We got a problem. 3 of you. It's worse than I thought. So indeed, you know, we claim to be interdisciplinary and hybrid, but we're so ghettoized it's not funny. So is science in trouble? Okay, I'm going to wrap up now because otherwise Jack Ox is going to yell at me because Ursanada is coming on next. So I just want to close this, this line of sort of this narrative with, I guess as a scientist who's worked in science for many, many decades, I guess I wonder whether we're at a point of rupture. I grew up at the time of when Vannevar Bush and Science, the Endless Frontier was up there. Science and technology were going to lead to full employment and a more fruitful life. There's probably no more than 2% of the world population that believes that today. I'm not exaggerating much. Science doesn't seem to make political sense at the moment. Alan Leshner, who's the president of the American Association of the Advancement of Science this January, he just come out of the budget battles in the US Congress, and he said discreetly, the link between science and the rest of society is a little fragile these days. Come to Dallas sometime. So indeed, I think there's a deep underlying problem, which is a cultural issue, which is science culturally embedded in a robust way? Helga Novotny, the president of the European Research Council, has been writing about this at great length, where indeed her feeling is that there's a fundamental rupture between science and society that's occurring. So that's a little bit pessimistic. Thank you for inviting me. The delight is there are so many of us here now. Art science technology is thriving and growing, and I look forward to meeting you in Sydney. Thank you.